All right, so we left off here with groundwater. So again, this picture just shows the confined aquifer or artesian aquifer. It also starts to introduce the equation for calculating the speed that water is moving through the ground. We see that that's a function of the difference in elevation from one point to another, the distance between those 2 points, and the circumference of the well itself. All right, so it's this picture that I wanted to focus on a little bit more. So here we have two homes side by side. We have wells from each of the homes. You can see that one well is drilled to a greater depth than the other well. Again, for those of you that have or will live in a house with a well, that's something to be aware of or concerned. Oftentimes on the well itself, it will tell you the depth that it has been dug to, and it will also have the flow rate, and that's going to vary from house to house. And it matters in a situation like this where you're essentially drawing from the same water supply as all the other homes in the area. And so this can have an effect on your well during times of drought. You can see that this well creates this cone of depression. See in the house, the yellow house here. In this case, it's not affecting the house to the left, so it's not a problem. But you can also see that the yellow house isn't drilled to a greater depth, so in effect, the house on the left could pull down the water table so that the house on the right does not have access to water. So we see that here as well. During times of abundant rainfall, when there's recharge going on, it's not as much of a concern during the wet period as during a dry period. And so that cone of depression is being formed by the well. Again, we can see this in groundwater models that we can use in class. These are just plexiglass models that contain different arrangements. They have impervious surfaces in them. They have these wells drawn in, and you can put in different dye, and that dye will move through the water. So you can actually see these cones start to form in these models. So here's a dry period where again, the house on the left does have access to the water, but the house on the right now has a dry well. All right, so this would be the concern for those with wells during dry periods, especially when your neighbor may be using more water than they should. All right, the other thing to note, although this doesn't show it, is that the stream is often fed by the groundwater, and so the groundwater is percolating up through the ground, so that water table is sometimes within the stream itself. And so even in dry conditions where you would think it hasn't rained for a while and the stream should not have much water in it, that groundwater percolating up through continues to cause the river to flow. All right, so when we're talking about trying to get water to the well for drinking water, for water for your house, having high permeability and porosity are a good thing, right? And so that means the water will flow to your home quickly. But there are conditions where that is not advantageous, where you wouldn't want water to flow as quickly. So again, calculating that is an important thing that we can do with some mathematics. By just having the general rate. So thinking about when it's not advantageous, when there's pollution in the ground, right? And so when there is a contaminant in the ground, that's when you would not want the water to move faster through the ground, because it's going to move that pollution closer to a source like your well. Right? And so there's a variety of both point source and non-point source contamination that we see in this picture that can infiltrate groundwater. Some things like surface, like landfills and pesticides on crops, sewage treatment plants. Here we have an underground gas tank. So this happened, it's been about probably 15 years ago up in Falston, Maryland. This exact scenario happened where the storage tank of an Exxon station leaked into the ground, and the surrounding homes all had wells, so they all had to put abatement systems in. It was a huge mess because a lot of those homes were fairly pricey, $500,000 to $1 million homes, and that's not great for resale rate to have this abatement system in. So these do unfortunately happen from time to time. And then some things are continuously happening. Here we have salts on the highway, which happens every winter, although we had a mild winter this last winter. A lot of the geology faculty here at Towson study this very thing. Right. So here's that plume of, in this case, gas that is moving with the natural flow of groundwater. Right? And so being able to calculate that flow of groundwater is important. It's important for you to get fresh water, to know how much you're drawing from or what the rate of that flow is. But in this case, it's also important to calculate how long it's going to take this leak to reach a certain point. You can see here that depending on a lot of factors, in this case whether it's just shallow or deep, the amount of time that water spends in the ground can vary a good bit, and that's because of the flow rate. Right. So I'm going to just sort of go through this rather quickly. Again, I'm not going to ask you to calculate this groundwater flow rate, but we can do it. Again, you can see here the amount of time that it takes water to flow through, just in general terms of centuries, millennia, or years. But we can calculate that. All right, so this is done with Darcy's law, and I'll just run through the equation real quick so you can see how it's done. This is basically the scenario that you have. Well A, well B, we know the cross-sectional area of those wells. We know the vertical drop from A to B here, so from this point to this point, and we know the flow distance between the two. So we can use this equation, and again, like all equations, it can be manipulated to determine different things. So the volume of water, the cross-sectional area of the flow, the permeability of the aquifer, which is often what we're trying to solve for, the flow distance, and the height. All right. Like a lot of equations, sometimes different letters are used. All right, so here the hydrologic gradient, or the difference between the two, again, H1 to H2, and then the length between them. All right, so I'm not going to ask you to calculate those for class, but that is something that you can do to calculate flow rate. So that's it for groundwater. See you all next time.